So we're going to show that for all positive a, b, and c, a to the 5 minus a squared plus 3 times b to the 5 minus b squared plus c times c to the 5 minus c squared plus 3 is greater than or equal to a plus b plus c all cubed. So first, the most important observation of this problem is to notice that a to the power of 5 plus 1 is greater than or equal to a cubed plus a squared for all real numbers a. Now there are many ways to prove this, but my choice is going to be weighted AMGM. For those of you who are unfamiliar, AMGM states that a1 plus a2 plus all the way to an, all divided by n, is greater than or equal to a1 times a2 times all the way to an, all to the power of 1 over n, or to the nth root. Now, a special strategy that can be used for solving AMGM problems is taking weighted AMGM. So for example, if I have 3x as one of my terms, I can split it into x, x, and x, and then apply it as 3 separate terms. This will then allow me to get a different power here or a different denominator here. Well, in this example here, I'm trying to show that a to the 5 plus 1 is greater than or equal to a cubed plus a squared. And so, what if I separated this into two terms? So a to the 5 plus 1 is equal to 2 over 5 times a to the 5 plus 3 over 5 plus 3 over 5 times a to the 5 plus 2 over 5. So let's take these two terms at a time and these two terms at a time and then apply them into AMGM. So I have 1 over 5 times a to the 5 plus 1 over 5 times a to the 5 plus 1 over 5 plus 1 over 5 plus 1 over 5 all divided by 5 is greater than or equal to the fifth root of 1 over 5 times a to the power 5 times 1 over 5 times a to the power 5 times 1 over 5 cubed. So now multiplying both sides by 5 and then taking out the 1 over 5 over here gives us 2 over 5 times a to the 5 plus 3 over 5 is greater than or equal to the fifth roots of a to the 5 times a to the 5. And so we have 2 over 5 times a to the 5 plus 3 over 5 is greater than or equal to the fifth root of a to the power of 10, or a to the power of 2. So now using the same logic for 3 over 5 times a to the power of 5 plus 2 over 5, we get 1 over 5 times a to the power of 5 plus 1 over 5 times a to the power of 5 plus 1 over 5 times a to the power of 5 plus 1 over 5 plus 1 over 5, all divided by 5 is greater than or equal to the fifth roots of 1 over 5 times a to the 5 squared times 1 over 5 cubed. So now doing the same thing, multiplying both sides by 5 and then taking out the 1 over 5, we get that 3 over 5 times a to the 5 plus 2 over 5 is greater than or equal to the fifth root of a to the power of 15, or a cubed. And so now adding these two up, we get a to the 5 plus 1 is greater than or equal to a cubed plus a squared. So now we have proven the above. So now let's turn this term into this term. Subtracting a squared from both sides, we get a to the 5 minus a squared, and then adding 2 to both sides gives us plus 3 is greater than or equal to a cubed plus 2. And now applying the same to b and c, it then suffices to show that a cubed plus 2 times b cubed plus 2 times c cubed plus 2 is greater than or equal to a plus b plus c cubed. So now we can apply Hölder's inequality over the sets a1, 1, 1b1, and 1, 1c to get that a cubed plus 1 times b cubed plus 1 times c cubed plus 1 is greater than or equal to a plus b plus c all cubed. Now this is equal to the above. And so now we have proven the above statement, which also proves the initial statement. And so we are done. Now briefly, I'm going to explain what Hölder's inequality is. Now, Hölder's inequality is a special case of the Cauchy-Schwarz inequality. Now, the Cauchy-Schwarz inequality states that for all sets a1 to an and b1 to bn, we know that a1 squared plus a2 squared all the way to an squared multiplied by b1 squared plus b2 squared all the way to bn squared is greater than or equal to a1 b1 plus a2 b2 all the way to an bn all squared. Now, Hölder's inequality is a generalization of this statement. Now, Hölder's inequality can be applied to any power. So Hölder's inequality is a generalization of Cauchy-Schwarz that can be applied to any number of sets over that number of power. But in this case of the Hölder's inequality, and the most common case of the Hölder's inequality, we are going to use 3 sets. So it then goes that Hölder's states that a1 cubed plus a2 cubed plus a3 cubed all the way to an cubed times b1 cubed plus b2 cubed plus b3 cubed all the way to bn cubed times c1 cubed plus c2 cubed plus c3 cubed all the way to cn cubed is greater than or equal to A1B1C1 plus A2B2C2 plus A3B3C3 all the way to AN, BN, CN, all to the power of 3. And so as we saw earlier, we applied Hölder's inequality to this problem using the sets A1, 1, 1B, 1, and 1, 1C. Alright, so that's about it. Thanks for watching, hopefully you enjoyed it, and hopefully I'll see you next time.